axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead. For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. I have represented the internal forces as 4 separate forces here, but I could have represented them as 1 or even 20 forces. In reality, the internal forces are distributed over the entire surface of the cross-section. For this reason, it doesn't make much sense to talk about specific internal forces. Instead, it is better to talk about stress. Stress is a quantity that describes the distribution of internal forces within a body. It makes it easier to discuss the internal state that develops within a body as it responds to externally applied loads. Stress is a measure of the internal force per unit area, and so has units of newtons per meter squared in SI units, and pounds per square inch in US units. Newtons per meter squared are also called pascals. In the case of our axially loaded bar, the internal forces are acting perpendicular to the direction of the cut we made. This type of stress is called normal stress. We can calculate the normal stress in our bar as the applied force F divided by the cross-sectional area A of the bar. It is denoted by the Greek letter sigma. One reason being able to calculate stresses is important is because it allows us to predict when an object will fail. Let's say our bar is made from mild steel, which has a strength of 250 megapascals. The bar will fail when the stress within it exceeds the strength of the material. If our bar has a diameter of 20 millimeters, for example, we can calculate that it will fail if the applied force is larger than 79 kilonewtons. Normal stress can be either tensile or compressive. In this case, the stress is tensile, because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. Used is that tensile stresses are positive values and compressive stresses are negative values. In the case of our bar, it is reasonable to assume that the stresses are distributed uniformly across the cross-section and along the length of the bar. But this is a very simple scenario. The stress distribution in a beam that is bending, for example, will be more complex. Stresses will be tensile on one side of the cross-section, but compressive on the other. Strain is a quantity that describes the deformations that occur within a body. If we fix our bar at one end and apply a force to the other end, the force will cause the bar to deform. The normal strain within our bar associated with this deformation can be calculated as the change in length of the bar delta L divided by the original length L. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strains can be tensile or compressive. I mentioned earlier that the concepts of stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. We can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Stress-strain diagrams for ductile materials, like this one, show that there is an initial region for low strain values where the relationship between stress and strain is linear. Deformations occurring in this region are fully reversed when the load is removed, and so are said to be elastic. This linear relationship between stress and strain is defined by Hooke's law. The ratio between stress and strain is called Young's modulus, which is an important material property. Hooke's law usually only applies for small strains. For larger strains, the relationship between stress and strain is no longer linear. Deformations are not reversed when the load is removed, and we have permanent plastic deformation. You can learn more about stress-strain curves in my videos about Young's modulus, and about material strength, ductility, and toughness. So far, we have only talked about normal stress, which is stress acting perpendicular to a surface. The other type of stress is shear stress. If our bar isn't loaded along its axis, but instead perpendicular to its axis, like this, the internal forces that develop within it are oriented parallel to the bar's cross-section. These internal forces are called shear forces. Shear loading is common in bolts, for example.
मेरे बेटे जोरावर के खून में ही टेक्नोलॉजी है। आज के टाइम का बच्चा अभी से ही कोडिंग सीख रहा है। अब आप बोलोगे कि इतना छोटा बच्चा और अभी से ही फ्यूचर रेडी, बहुत नाइंसाफी है। अब तो एजुकेशन मिनिस्ट्री ने भी बोल दिया है कि बच्चों को स्कूल में कोडिंग सिखाई जाए। आज ही whitehatjunior.com पे क्लास बुक करो और फिर देखना, लोग कहेंगे इतना छोटा बच्चा और अभी से फ्यूचर रेडी। बढ़िया है। अपने बच्चों को कोडिंग सिखाओ और हल्ला बोलो।
Once again, it is helpful to use the concept of stress to talk about the internal shear forces within the bar. Shear stress is denoted by the Greek letter tau and can be calculated in a similar way to normal stress as the applied force F divided by the cross-sectional area A. This is actually an average shear stress, since the internal forces will not be distributed evenly across the cross-section. We can better understand shear stresses by looking at the stresses acting on a small element within our bar. We have a shear stress on one face of the element, but the element needs to be in equilibrium, so we must also have shear stress on the opposite face, in the opposite direction. And to maintain rotational equilibrium, we must also have two additional shear stresses, as shown here. These four stresses all have a magnitude equal to tau, and define the shear stresses acting.
Good evening. Good evening, Maruti. Yashwant, good evening, Yashwant.
గుడ్ ఈవినింగ్ సార్.
ఇంతేనా వచ్చేది క్లాస్కి? మీ క్లాస్లోకి ఇంకెవరైనా వస్తారా?
సార్ నిన్నైతే వచ్చారు సార్ ఒక 10 మెంబర్స్. ఈ రోజు ఇంకా ఏమో సార్ రాలేదు ఎవరు.
చూద్దాం, ఒక 5 minutes చూద్దాం, తర్వాత చూద్దాం.
ఓకే సార్.
So good evening to all. Only 5 people have only attended the class. So I was going to start the class now. So I observed last previous GATE question papers. 6 to 8 marks weightage will given to mechanics of solid subject. And here they are giving generally simple problems. In the first unit, generally they given the problems on elastic constants and problem on stress strain curve. Generally, these are the things that will given in the from the first unit. So, are you hear me? Are you hear me? Say something. Are you hear me? Yashwant?
sir.
Maruti? వాయిస్ వినపడుతుందా?
సార్
ఓకే. So these are the main outlines of that MOS. These outlines are prepared by seeing that present year GATE syllabus. The first topic is stress and strains, elastic constants, Poisson's ratio. I'm assuring that from the first 4 topics, you will get 1 or 2 questions, either 1 mark or 2 marks question. So next one, strain gauges and testing of materials with using UTM, testing of hardness by using impact strength, and more circle, thin cylinders, SFD, BMD, bending stresses and shear stresses, torsional stresses, Euler's theory, and energy methods. These are the content we need to prepare for your GATE exam for MOS subject. Next, what is meant by stress and strain? So generally stress is nothing but a resisting force is set up in the component. So it called as stress in generally. So when the material is subjected to an actional force, a resistance force is set up within the component because of due to equilibrium of force, some body is subjected to some external load. You need to maintain same condition. It need to apply opposite reaction force also. So that is called resistance force. That intensity force distributed over a given section is called as stress at a point. So the resistance force acting on a particular cross section distributed on a particular cross section is called as stress. In mathematically, stress is defined as load by area. It is denoted with letter sigma. Sigma is equal to P by A. Let us take this is a object. Load P is acting on both sides. I'm pulling this force P towards outside of the object. This particular surface, this particular cross section will be subjected to forces. See this diagram. So this is called cross sectional area. Which direction is force is acting? Which plane is force acting? That particular area you need to consider for the calculating of stress value. stress is equal to P by A. P is the external force acting on the member. Generally, it is noted in letter Newton, letter with capital N. Area, cross-sectional area, generally we rotate with capital A. And units are meter square. Then the force unit is equal to Newton per meter square, all Pascal. So we need to know conversion is very, very important for calculating of the problems or in your ways. 1 kilopascal equal to 10 power 3 Pascal, that is equal to 10 cube per Newton meter square. You need to remind 1 point, 1 megapascal equal to 1 Newton per mm square or 10 power 6 Newton per meter square. 1 gigapascal equal to 10 power 9 pascals or 10 power 9 Newton per meter square. These are the conversion must be remain in your mind while doing solving the problems. So 1 kilopascal is equal to 10 power 3 Newton per meter square. 1 megapascal equal to 10 power 6 Newton per meter square. 1 gigapascal equal to 10 power 9 Newton per meter square. We know that we need to know generally we solving the problems in terms of mm square. So 1 megapascal equal to 1 Newton per mm square. See, let us see. A rod is having 10 mm into 10 mm size cross section, is carrying an axial tensile load of 10 kilonewtons in this rod. What is the tensile stress developed in the material? When I am going to solve the problem, first you need to check the unit system. We need to maintain same unit system for solving the problem from first to last. You want to use loads in Newton, you need to use load in Newton all the parameters. Where you can get the load, all that parameters you need to use Newton only. For area, meter square means meter square or mm square means mm square. So we need to calculate the value. The problem is given a 10 into 10 cross section bar is subject to axial tensile load of 10 kilonewtons. What is the stress developed in the material? We know that stress is equal to load by area. So load, I know that 10 kilonewtons. I want to convert this 10 kilonewtons to newtons. 10 into 10 cube newtons. So 10 into 10 is 100 mm square. So 10 into 10 cube by 100, it gives 100 Newton per mm square. 100 Newton per mm square is equal to 100 megapascal because of 1 megapascal equal to 1 Newton per mm square. So like this, we are going to calculate the stress values. So what is mean by tensile stress? What is mean by compressive stress? And what is mean by shear stress? Tensile stress is nothing but it is always greater than or equal to 0. Sorry, always it is greater than equal to 0. Tensile stress is always greater than equal to 0. Here the stress is acting outside the object. So this force is acting outside the object. That force is called tensile force. Due to this force, what type of stresses are developed in the material, that stress is called as tensile stress. We need to remind one point. Here tensile stress is always greater than 0. Next, compressive, it is less than 0. Sigma less than 0. Always the force is acting towards the object. Adi outside the object, is towards the object. So when that force is acting inside the object, the bar member is going to reduce this length. So then automatically the negative force is induced in the material. So that's why I'm saying that sigma is less than 0. Then come to shear force. What is mean by shear force? So shear force is nothing but force is acting so here shear force nothing but the force is acting on the surface of the member. Here the force is moving towards outside or inside, but here the force is acting on the surfaces. Then it's called as shear force. Due to the force, what type then generally stresses are developed. That stresses is called shear stresses. Here also load by area only formula. But here we need to consider the area is surface area, not cross-sectional area. We need to consider the surface area of the object. That is called shear stress. Next, strain. Strain is nothing but generally change in length by original length. When the member is subjected to some force, due to that force, the member is going to decrease in length or increase in the length. So we need to calculate the strain means we need to get the formula from strain is equal to change in length by original length. This is the object. It is subjected load P. Due to that load acting on the member, this bar length is increased in the length of delta L. Then what is the final length of the member? So L naught plus delta L is the final length of the member. So we need to calculate the change in length. Minus L naught is equal to, it gives delta L. So delta L by original length is equal to L naught. So from that we are going to calculate the strain values. For the strain, we don't have any units for the strain. For stress, we have a megapascal, Newton per meter square, and Newton per mm square. Coming to strain, there is no units. It is a dimensionless quantity. Why? Because change in length is always measured in terms of meters or mm. Original length also you need to measure in meters and mm. So mm is going to cancel. We get there is no units for the strain. So strains also for three types. First one, tensile strain, compressive strain, and shear strain. As usual, similar the definitions for the stresses. Then here there comes the topic of true stress and true strain. Here stress is defined as the ratio of load to the cross section at any instant, then is called as true stress. At any instant, not final, not starting. At any instant, we are going to calculate the stress, that is called as true stress. So at any particular point, so if the volume of specimen assumed as a constant during the plastic deformation, is called as true strain. So before going to in-depth discussion of true stress and true strain, we need to know the stress-strain relation. What is the relation between the stress and strain? This relation is derived by the Hooke's law. Hooke's mathematician scientist, he derived the equation for stress and strain. He derived the relation between stress and strain. Stress is always directly proportional to the strain up to elastic limit. He is given a statement. How he given the statement? So first he test for linear elastic materials. In that linear elastic materials, one of the strain is proportional to stress. How I am telling that? He taken the elastic material, he applying the load continuously on the member. So first 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Like that, your curve will be, your line will be drawn this. So after that, apply the load, but it is not going to regain its original shape. So means it lost its elastic property. Means that is that point that failure will start, where the failure will occurs. That point is called yield point. So a point దగ్గర నుంచి failure అనేది start అవుతుంది. So this is the curve we generally get for linear elastic materials up to elastic region. So suppose I am taking as a rigid material. Rigid material మీద ఎంత లోడ్ వేసా కానీ లోడ్ పెంచుకుంటున్నా పోతున్నా కానీ స్ట్రెయిన్ వస్తుందా రాదా? What is mean by rigid material? First of all, can anyone respond? Can anyone respond? Rigid material. Can anyone respond? What is mean by rigid material? So rigid material nothing but is a material when applying the load on the object, it is not going to under the deformation. It is not going to undergo the any deformation, then called as rigid material. మనం ఎంత లోడ్ వేస్తా కానీ ఎటువంటి చేంజ్ ఉండదు దాంట్లో, అటువంటి మెటీరియల్స్ ని రిజిడ్ మెటీరియల్స్ అంటాం. సో ఐఎమ్ డూయింగ్ ఫర్ స్ట్రెస్ స్ట్రెయిన్ టెస్ట్ ఫర్ దట్ రిజిడ్ మెటీరియల్. ఐ అప్లైయింగ్ ద లోడ్, దేర్ ఇస్ నో చేంజెస్. So you are applying the load, that y-axis line will be going to increase like this, but in x-axis nothing will happen because of it is a rigid material. The displacement is equal to 0. Next comes to perfectly plastic non-strain hardening material. If you take plastic material, when I applying the load continuously on the body, generally not going to any deformation. మీరు ఇంట్లో ఒక ప్లాస్టిక్ బిందె తీసుకోండి, లేదంటే ఒక ప్లాస్టిక్ ఆబ్జెక్ట్ తీసుకోండి, లోడ్ అప్లై చేయండి, ఎటువంటి చేంజెస్ ఒక పర్టికులర్ లోడ్ వచ్చిన తర్వాత ఇట్ ఈస్ గోయింగ్ టు డిఫార్మ్. ఆ కాన్స్టెంట్ లోడ్ దగ్గర కంటిన్యూస్ గా డిఫార్మ్ అవుతుంది. దట్ ఈస్ కాల్డ్ పర్ఫెక్ట్లీ ప్లాస్టిక్ మెటీరియల్. నెక్స్ట్ రిజిడ్ ప్లాస్టిక్ మెటీరియల్. వాట్ ఈస్ మీన్ బై రిజిడ్ ప్లాస్టిక్ మెటీరియల్? Here also rigid plastic material up to certain stage no deformation will comes on the plastic material when the load is increasing. After a certain point it continuously without taking the load continuously it is going to increase in the length or width or something. So means we are getting strain without acting on the load. So elastic perfect plastic material. So up to certain stage it having it exhibit elastic stage. It is something load, it will continuously go for plastic. It is called perfect plastic material. So here without increasing the load, but your strain value is going to increase. This type of material is called elastic perfect materials. So this is the form for elastic plastic materials. So generally it is come for ductile material. This type of curves are generally come for ductile materials. We'll see next slide, next coming slides, stress strain curve detailedly. Are you hearing me? Are you hearing me?
Sir, yes, sir.
But response లేదని అడిగినప్పుడల్లా
సార్
అడిగింది
గుర్తు రావట్లేదు సార్.
రిజిడ్ మెటీరియల్ అంటే ఏందో అడిగా, అది కూడా తెలియదండి, నేనేం చెప్పాలి?
రిజిడ్ అంటే డిఫార్మ్ అవ్వదు సార్.
Okay, good. So now I'm going to play some video for you for stress strain curve for tensile material. So it's simultaneously the experiment also going on. Just you watch that video, you will get better explanation.
To a deforming force, a restoring force is developed. Stress strain curve. In this module, you will learn how strain changes with changing stress for different types of materials. When a body is subjected to a deforming force, a restoring force is developed in the body which is equal in magnitude but opposite in direction to the applied force. This restoring force per unit area is known as stress, and the deformation caused is known as strain. The relation between the stress and the strain for a given material can be found experimentally. For this, let us take a spring and stretch it by applying a force. This causes a change in the length of the spring. Now change the force applied and again note the change in length of the spring. Record the fractional change in length, that is, the strain, for the different values of force. Plot the graph between the stress equal to the applied force per unit area and the strain produced. The curve so obtained helps us to understand how a given material deforms with increasing loads of force. From the graph, we can see that in the region between O to A, the curve is linear. In this region, Hooke's law is obeyed. That is, stress and strain are directly proportional. That is, with increase in force or stress, the strain also increases. The body regains its original dimensions when the applied force is removed. In this region, known as elastic region, the solid behaves as an elastic body. In the region from A to B, stress and strain are not linearly proportional. In spite of that, the body returns to its original dimension when the load is removed. The point B in the curve is known as yield point, also known as elastic limit, and the corresponding stress is known as yield strength, Sy, of the material. If the load is increased further, the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. It is represented by the curve BD. When the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this case, even when the stress is zero, the strain is not zero. The material is said to have a permanent deformation or permanent set. This deformation is said to be plastic deformation, and this region is said to be plastic region. The point D on the graph is the ultimate tensile strength, Su, of the material. Beyond this point, additional strain is produced even by a reduced applied force, and fracture occurs at point E. If the ultimate strength and fracture points D and E are close, the material is said to be brittle. Some examples of brittle substances are glass, slate, antimony, and bismuth. If the ultimate strength and fracture points D and E are far apart, the material is said to be ductile. For example, aluminium, copper, and steel. The stress-strain curve varies from material to material. This figure shows
So you just in that video, what you observe? Can anyone give a response for my question? What you observed in that video? Please respond. Please respond. So in that video, we seen that when let us take one spring, mild steel spring, he applied certain load on the spring, it will deform up to certain limit. It regains its original position from point one point to another point. After that, I applied another extra load on that material. It going to extend at a certain portion. It is not going to regain. At that particular point in that video, he clearly mentioned for you.
it by applying a force. This causes a change in the length of the spring. Now change the force applied and again
So this is the
note
change in
in length of the spring. Record the fractional change in length, that is
So
the
first
strain
one length,
for the
one load,
different
second load,
values
third
of
load.
force. Plot the graph between the stress equal to the applied force per unit area
So first
and the strain produced.
up to this point, that region is called
The
elastic
curve so
region.
obtained helps us to understand how a given material deforms with increasing loads of force. From the graph, we can see that in the region between O to A, the curve is linear. In this region, Hooke's law is obeyed. That is, stress and strain are directly proportional. That is, with increase in force or stress, the strain also increases. The body regains its original dimensions when the applied force is removed. In this region, known as elastic region, the solid behaves as an elastic body. In the region from A to B, stress and strain are not linearly proportional. In spite of that, the body returns to its original dimension when the load is removed. The point B in the curve is known as yield point, also known as.
So in that video, this is that your stress strain curve. So this is your strain, this is your stress. Generally we plot strain in x-axis, stress in y-axis. So here they first applied a load on that spring material. Due to that applying load, it causes some deflection. So he measured the strain on that spring. He plotted a curve between that points. So a line up to this point A. After removing the load, it regains its original position. That point is called lower yield point. So up to this, it called elastic region, elastic limit. ikkadi varaku unde point one elastic point anta. Then after that, I applied some load on that same spring. Due to that force, that it going to deform some distance, but this portion is not going to regains. So that point we recorded as the B, that is called upper yield point. Up to that point, it regains its original position up to certain limit. So this portion is called transition stage between elasticity and plasticity. So after that, I applying some another load on that particular material. What will happen? It continuously going
Elastic
to.
limit and the corresponding increased further, leads the yield presented by the curve. The body does not regain its
So after applying some load, once again, after
original
reaching this point,
dimension. In this case,
after reaching the point, after reaching this point, once again I apply the load on the material, it is going to deform. This particular portion is called as plastic state or plastic region. So after that, I applied another some load on that material. It will going to deform continuously without changes of minimum amount of load. It will going to deform more. Some cases we are not applying any load, but it is going to deform. So at particular point, it is going to fail.
even when the stress is zero, they have a permanent to be plastic region. Beyond this point, if the ultimate strength
See,
and fracture
this point
points
we are
D
getting
and E
fracture.
are close, the material is
ఈ
said
రెండు
to be
దగ్గరగా
brittle.
ఉన్నాయనుకోండి,
Some
దాన్ని brittle
examples of
material
brittle
అంటాం.
substances are glass, slate, antimony, and bismuth.
Without any
If
warning,
the
the
ultimate
material is going
strength
to
and
fail. Then we
fracture
called
points
as a
D and E
brittle material. Without any warning, if the material is going to fail, that material is called brittle materials. With having some dangerous shown, that change in the length shows up to after that some point it will going to fail. That material is called ductile materials. In the graph will show that DE is nearby, then it is called brittle materials. It have some distance between D to
are
E,
far apart,
we
the
called as
material is said to be
ductile
ductile.
materials.
For example,
Are ductile substance materials. Example, steel materials is the best example for ductile. What is meant by ductile property? What is meant by brittle property? Ductile property is nothing but is drawn into wires. Brittle properties is not going to dry, it is going to direct to get failure. Nothing will changes will happen that up to certain limit. When it reaches to maximum ultimate load, will get direct failure. That substance is called brittle materials. So this is the generalized stress strain curve for mild steel materials.
aluminium, copper, and steel. The stress strain curve varies from material to material. This figure shows the stress strain curve for the rubber. Although elastic region is very large, the material does not obey Hooke's law over most of the region, and there is no well-defined plastic region. Substances like rubber, which can be stretched to cause large strains, are called elastomers. Interestingly, the elastic tissue of aorta present in our heart is also an elastomer. Let's recap. The stress strain curve varies from material to material. The stress strain curve of a material has.
So ఇక్కడ చూడండి. So this is a curve for plotted for rubber band. So ఈ రబ్బర్ బ్యాండ్ లో at regains its original position, but it is not going to obey the Hooke's law. సో ఈ విధంగా ఉంటుంది. ఇట్ ఇస్ బికాస్ ఇట్ ఈస్ వేరీ ఫ్రమ్ ద మెటీరియల్ టు మెటీరియల్. స్ట్రెస్ స్ట్రెయిన్ కర్వ్, స్ట్రెస్ స్ట్రెయిన్ కర్వ్ అనేది ఎప్పటికీ కాన్స్టెంట్ కాదు, మెటీరియల్ ని బేస్ చేసుకొని స్ట్రెస్ స్ట్రెయిన్ కర్వ్ అనేది వేరీ అవుతూ ఉంటుంది. సో ఫ్రమ్ దిస్ వీడియో we know that some points
substances like present in our material has the following regions. Elastic region, where the body regains its original dimension applying force, where additional strain is produced even by
these are the silent features is there in your material. First, generally the stress strain curve is varies from metal to metal. Stress strain curve metal has the following regions. First one region is elastic region, where the body it regains its original dimension. When applied force is removed from the material, it is going to regains its original position. A particular point work it regains means up to elastic region వరకు దాని ప్రాపర్టీస్ ని అది రీగెయిన్ చేసుకోగలదు. Then when applying the force, once again applying the force on the body continuously, it is going to permanent deformation. ఎక్కడ permanent deformation వస్తుందంటే then we called, that is the reason is called as plastic region. So where that material is going to break or fracture, that region is called fracture region. The 3 points are the silent features in that material, in the stress strain curve. Based on these points only we are going to differentiate it is a ductile material or brittle material or a rubber material.
by a reduced applied force and fracture points lie close to each other. If the ultimate strength and fracture points are far apart, substances which can be stretched to cause large strains are called elastomers.
This is about the stress strain curve. Can anyone tell me what is mean by Poisson's ratio? What is mean by Poisson's ratio? What is mean by Young's modulus?
Sir, Young's modulus is the ratio between stress and strain, sir.
So it is the ratio between stress and strain. Young's modulus is the E is the constant, Hooke's law constant. In from the Hooke's law, it says that stress is directly proportional to strain within the elastic region only. Within the elastic region, stress is directly proportional to strain. So that proportional constants we replace with Young's modulus letter, that is capital E. Capital E is equal to stress by strain. Can anyone define what is mean by Poisson's ratio? Poisson ratio.
It is the ratio to the longitudinal strain to the lateral strain, sir.
What is mean by longitudinal strain and what is mean by lateral strain?
Longitudinal strain means if the load is acting axially to the body, sir.
Okay.
If the load is acting perpendicularly to the axis of the body, sir.
Okay. So I'm going to give 1 minute video about it provides better explanation for Poisson's ratio. You just watch that video and after that you tell me what you understand from that video. So because of in every maximum within the maximum time they are asking Poisson's ratio and Poisson's ratio values for the different materials. I will give what are the values are varying from the material to material, Poisson's ratio values and Young's modulus values. Generally they are asking for 1 mark question in your GATE examination.
An example of a rubber strip as shown. When we pull this strip in a longitudinal direction, the strip elongates in a longitudinal direction and contracts in a lateral direction. The strain developed in a longitudinal direction is known as longitudinal strain, and the strain developed in a lateral direction is known as lateral strain. Now, when we take the negative ratio between this lateral strain and the longitudinal strain, we get Poisson's ratio. Poisson's ratio can be represented as Poisson's ratio describes the relative change in the lateral dimensions of an object. when the load is applied in longitudinal direction and vice versa. Poisson's ratio for some of the important materials are as shown. Poisson's ratio to understand longitudinal direction and contracts in a lateral direction. The strain developed in materials are as shown.
So in that video,
Poisson's ratio. To understand Poisson's ratio, let's take an example of a rubber strip as shown. When we pull
in that video, he's taken rubber strip. He pulled in x-axis direction, x direction.
the strip
So
in
due
a
to pulling of
longitudinal
the
direction,
material, rubber
the strip
material,
elongates in a
this
longitudinal
x direction,
direction
the length
and
was going
contracts
to
in a
increase,
lateral direction.
and lateral dimensions will going
The
to
strain developed
reduce.
in a longitudinal direction is known as
From this, I'm going
longitudinal
to define
strain.
Poisson's ratio is
Is known
nothing but
as lateral. When
lateral
we take the
strain by
negative ratio between
linear or
this lateral
longitudinal
strain and the
strain.
longitudinal,
It gives Poisson's ratio. So it is a main very important when the calculate the forces stresses in 3-dimensional. For 2-dimensional, it is not that much important. If we go for calculating the stresses in 3-dimension, you must be consider the Poisson's ratio. If you consider the xy only, generally in the z direction also some of the forces will causes. Due to that forces, stresses will be developed in the material. So the 3-dimensional equivalent stresses is called as Wien-Messes stresses antam. 3-dimensional equivalent stress is called as Wien-Messes stresses. So it is plays main role for calculating the formula for Wien-Messes stresses. So we'll see where we can use this Poisson's ratio value. Generally, it is notated with letter mu.
longitudinal strain, we get Poisson's ratio. Poisson's ratio can be represented as
See,
Poisson's
that
ratio
rotating
describes
letter is mu. Mu is equal to lateral strain by or longitudinal strain. Lateral strain by or linear strain. So this is about Poisson's ratio. We'll see in the next class what are the values of Poisson's ratio we have. So thank you for attending the class. And once again, I'm telling that if the students are come regularly, then I will take the class. Otherwise, just tomorrow morning, I will going to tell to your in charge, Vamsi sir. Students are not coming, sir. I won't take any classes for GATE. Inform to your student, you inform to your friends. Attend the classes from next class onwards. I will take. Otherwise, I won't take the class.